Welcome to Natural Habitat Adventures, Daily Dose of Nature. Today's topic, what does climate change actually mean? Part 2, presented by NatHab Expedition Leader Kristina Disney. I'm your host, Rob Mess. Thank you all so much for being here today. Over to you, Kristina.
Thank you so much, Rob, and hello, everyone. Very happy you've come back for part 2, or if you're joining us for the first time today, we're very happy to have you step in. As he said, my name's Kristina. I've been a guide with NatHab since about 2018. Very excited to be going back for our Churchill polar bear season this fall. We're just getting some dates settled, and I got some emails, so it's looking exciting. But today we're going to talk about climate change, and somewhat as it does pertain to polar bears, but mostly as it pertains to our whole big wide world. And I'll just do a real short catch up. So last week we talked about mostly the history of our Earth and its climate, and that it has changed drastically since the formation of our big beautiful planet in various ways, some of them being quite extreme. And so a recent report came out from the IPCC, from the UN, talking about how we're on trajectory to change. We're on track to reach about a global warming of 1.5 degrees since the 1880s. And the reason why we talked a lot about Earth's history last time was to give some context to what's happening now. But for anyone who was following along last week, you'll realize that 1.5 is not really a huge change compared to some of the other changes that Earth has undergone. And so today we're going to sort of zoom the clock back up to today and the sort of recent history and the future to come, and see just exactly what that number and why it's so specific and what it means to us. But before I say what it means to us, I want to talk about what 1.5 degrees Celsius can mean for a sea turtle. So, sea turtles, it makes a huge difference because of their embryos and their eggs, because of the temperature of the sand when they lay their eggs. If it's warm, so if the sand temperature is around 31 degrees Celsius, then they tend to have only female green sea turtles. And if that temperature is closer to 28 degrees, 27.8, then they tend to have males. And so there's been a lot of research into how the warming of our climate might actually drive green sea turtles into extinction, because they're producing more and more females, and that the ratio is becoming more off. So it's a small example, but it's also a very significant one if you're a sea turtle, which we're going to go into some bigger ones today, right? But so the IPCC, I said it before, it's the Intergovernmental Panel on Climate Change. And in March, they came out with a synthesis report of a lot of work from thousands of scientists across the world of where we're at and how that change is really coming to play. And so the number that sort of the world has settled on is 1.5 degrees. If we hit it, there's a lot of things that we can't come back from, or at least not on the scale, certainly, of hundreds or thousands of years. And so that report that came out has a lot of information in it. And so part of why I was inspired to do this webinar specifically is because those are often presented in a rather dry, hard to reach way that doesn't get out beyond sort of the shoulders of scientists and governments and things like that. So sometimes it's good to see that in a different light. So I'm going to do a little bit of the drier reading, but I promise we'll break it down and look at it a few different ways. So this is from their Future Climate Change Risk and Long-Term Response, right? So I'm just going to read this one out for us. Continued greenhouse gas emissions will lead to increasing global warming, with the best estimate of reaching 1.5 degrees in the near future in considered scenarios and modeled pathways. Every increment of global warming will intensify multiple and concurrent hazards. Deep and rapid sustained reductions in greenhouse gas emissions would lead to a discernible slowdown in global warming within around 2 decades, and also to discernible changes in atmospheric composition within a few years, right? So this is kind of what I was saying when I was opening us up here, was that we are on a trajectory to reach this 1.5 degree warming, but we have this window of time, really between now and maybe 2035 and 2040, to actually change things before we cross the threshold. I often say that, you know, humans are a threshold species. We don't fix anything when it's bent. We only fix it when it's really broken. And we're at that bent phase, right? We're at the chance to sort of backtrack and change what we see and change how we can work with it. But I want to give us some context for this 1.5, right? Because 1.5 doesn't really produce an emotion or a feeling. It's just a number. So let's figure out how we got it and where it came from. So this is the temperature graph of the last 2,000 years or so. And what you're seeing in red is what has been actually measured since about the 1880s or so. And everything before that is what we've estimated as a proxy based on the records that we have. And that's sort of how everything works, right? You get a baseline, and you look at some other things corresponding to it, and then you can kind of map it out. And so one thing people always say is like, well, you know, there's a lot of uncertainty with that, right? And that's completely fair if we're looking at recent history, right? So that tan around on the graph that you're seeing that sort of bounces around with our black line is our estimated record. That's the uncertainty. And here's one sort of significant thing I want to point out is that, so, you know, in theory, some of these records that we have, they could have been much higher than what we thought they were. But if you look at where we are now, even with our wildest uncertainty, we have gone past that, right? So change is certain. That's one thing that we can stick with now. And so if we zoom in a little bit more here and we look at what's happened since the 1880s, and the reason why our benchmark is the 1880s is sort of twofold. One, it's when we were able to start measuring temperature with a precision that sort of everyone accepted and moved forward with, which you could say is somewhat coincidental with the fact that our ability to do so is also timed roughly with the Industrial Revolution. So is it a good time to be able to measure temperature precisely? Yes, but only because we figured out how to do it. It's a weird chicken and egg thing kind of happening there as far as technological development goes. And so I wanted to look at the last couple hundred years or so here, right? And give some sense of what's happening. So when we say 1.5 degrees, we're comparing it to the global average temperature, which in the 1880s was about 13.7 degrees. And Earth kind of hung out at that mean temperature from the 1880s to about the 1910s. And then you can see in the 1920s up to about the 40s that it shifted a little bit. It started going up, and it was warming at about 0.1 of a degree per decade. And it did that for a little while. So there's a big jump there, and then it sort of plateaued a bit until the 80s. And when the 80s hit, it started warming not at 0.1 degree every decade, but 0.2. And so it keeps growing and growing until you get up to where we are here in present day. So just to give you an idea, right? So if we look at the last 150 odd years of data that we have on these, the 10 warmest years have been in the last since 2010. Right? So 2022, the year that we just finished here, was the 6th warmest year on record in 150 years, right? And this is a big swing. And so that climbing that we've reached, right? That climbing at 0.2 every decade, right? So right now in the world, we're at about 1.1. So we need 2 more decades to reach 1.5. And that's this magic number, this critical number that they've all decided, that all these scientists have gotten together to say, hey, we don't want to reach that number. And so what I want to spend a little bit of time backtracking and giving some context to what 1.5 means, right? Because that's what's going to sort of drive home the picture for us. And in order to do that, we have to start filling in this empty globe, right? Because right now we're just kind of throwing down this number and saying it applies to the whole world. Excuse me. But that's an average, right? Averages are saying that there's actually going to affect the world at different rates in different places. And it's going to be much more extreme in some places. In some places, it's going to be really, really bad. And you could argue that in some places, maybe it's actually making that climate more hospitable, right? But we're saying it's an average effect is what we're looking at. And so if we're going to start filling up our globe, I want to make one more distinction, which is between climate and weather. And so we can define climate. It's always sort of funny. It's the weather conditions of a prevailing area over a certain longer time period. That's ultimately what only makes the difference between weather and climate. Climate is this long pattern that we've been looking at. In science, we often kind of do it in 30-year chunks, partially out of climate cycles, partially out of convenience and sort of having a standard, right? So if we try and split things up, right, weather is the behavior of your atmosphere or the atmosphere at any given moment. It can change really quickly from minute to minute, hour to hour. You're going from a blizzard to changing into sunshine, right? Things like that. Whereas climate is looking at these bigger trends over time. So obviously, that seasonality plays in, and whether you're living somewhere along the coast, right? So that's going to play into these longer trends that you're seeing. And the other thing that's important to think about is that, and this is true of weather too, but it's bigger picture climate, we want to think about this, is that all of it starts from the Earth's sun, but that's what kicks off our climate, right? It creates the heating, which is going to create the evaporation, which is going to start our whole weather systems to go, right? That's what's going to kick us off. But there's an interplay between all of the systems on Earth. It's not happening in isolation. It's not just the sun, right? The sun provides our initial energy, but then it's the interactions with our oceans and our glaciers and volcanoes that go off, putting particles in the air that change things, and how our organisms, right? They're the ones that are also going to affect our climate. So it's this big, big system. And so when we say climate change, we're not just, we've taken like this one piece of the pie, and we're saying that it's representing these changes to all of these systems. And I think we kind of, we use it as this big bracketing term that can get a little bit left behind. Oh, I should have put this. Oh, I just think this is a funny way to remember the difference between climate and weather before we go on. The weather is what tells you need to wear that day, and the climate is going to tell you how you're going to fill your closet, right? Right now, I'm currently in southern Saskatchewan, where it's windy and the snow is all melting, but I just came from Vancouver where I was in school, and there I have a bunch of rain clothes and umbrella. I wouldn't even use an umbrella here because the wind would blow it away. So it's something I've never even had out here, right? So things to put perspective on. All right, so we've got this big system that's at an interplay, and when we think about it, I could easily spend probably a whole month trying to work through all of these relationships and probably still not do them justice. So I'm going to stick to our atmosphere and stick to that portion of climate and its interactions and how it gets to be. And we will just sort of stick with the sun. But I just want, as I go through this next section, just keep in mind that there's all of these things, these feedback loops that come together and keep one another going, either negatively or positively, and reinforce that. But I want to take a second to really understand and I guess appreciate. This is one of my favorite things to learn and to teach in a lot of ways, because it sort of grounds our whole world in what we see and experience to what's happening to us. And I think that you can't always make those connections, so it's really great when you can. So when we talk about climate, I said the driver of our climate is the sun. The energy from our sun is what we get for photosynthesis. It's the source of all life on Earth, right? But it's our source of heat that's coming down that kicks off all of our systems. And the really important thing, right, the reasons why we have seasons is because the angle of the Earth, if you're on the north side, it's closer, it's warmer. If the south side is closer, it's warmer in the south and colder in the north, right? But so in general, the reason why that happens, though, it doesn't matter which way we're tilted, it's because of the angle that the energy from the sun is hitting us. So at the equator, it's getting a direct perpendicular hit. So all that energy is going to stay, whereas on the lower angle, some of it gets reflected and refracted and sent away back into space. And so even if it wanted to, the poles just can't heat up as much, right? But the equator is getting that direct light. And so that's what kicks off our initial global climate, because it creates this gradient from the center, from the equator to our poles. So if you kind of you can pick left side or right side, whichever. But if you look at the side, at the curve of the Earth, and it's got those red arrows pointing outwards, so that's the surface is heating and that hot air is rising up, and then it's all about balance, right? So something has to come in and replace that air. So the cold air from the north is going to come in and replace it, and it creates these units, these cycles. And so one way you can think about that is like a hot air balloon, right? They've got the heater at the bottom, it heats up the air, it goes to the top. And then when it gets to the top, it's away from that heater, from that flame. So it starts to cool down and it sinks and it returns, but then the heater's still there. And so it keeps heating up and keeps sending it. So that's kind of like this big current or conveyor belt of air that's moving around our planet, is the same way as this hot air balloon would work. Now, on our Earth, it's a pinch more complicated than a hot air balloon for many reasons. One of them is because we have the Coriolis effect, which Scouts Honor I will come back to and explain in detail in another webinar. But for this part, we'll just say Coriolis effect is because the Earth is spinning, right? And if we were a stationary object, that air would just move straight line north to south, but because we're spinning, the air ends up having to turn as well. And so it's trying to get north, but it can't take the straightest path, right? It's actually, yeah, because this is a whole fun topic and I want to go into it another time, but I'm going to leave it at that for now. So the idea is that it's spinning. And so you end up getting, it's one of the reasons why we have that notion of, countercurrent or counterclockwise and clockwise gyres, right? In our climates, north hemisphere, south hemisphere. That's because of the Coriolis effect, because it's sending these air parcels spinning away from the Earth as it's trying to reach that. And so if we hang on to this notion, one way when I was doing a lot of, or I guess I appreciated learning this way is because, it's so hard to understand our atmosphere that our instructors and our professors of the years would often call them parcels. If you think about a parcel getting moved around, it was easier than trying to just imagine a cloud, right? But the parcels mix and they change, but you can kind of think about them as a parcel, or in this case, a cell. And so as the air is trying to make that gradient and it's trying to go from the warmest spot in the equator to the coldest spot in the poles and cycle through, it goes through these other cells along the way because it doesn't get to go in a straight line. And so it creates these split of cells. So we tend to have, if we just cut the Earth in half, you've got 3 cells going north and then 3 sets of cells going south. And so you have a polar cell, a Hadley cell, a Ferrel cell and a Hadley cell. That's kind of what we sort of name them and break them up into. Right, and each one of those is like its own hot air balloon where it's sending it's along the surface, right, because it heats up above the surface, then it gets into high atmosphere where it's cold, there's more energy, it has to sink back down. And so that idea is what gives us our dominant winds, right, because they're cycling through one another. And this should kind of start, this is a really big picture, we're still looking at the Earth, but this should start looking kind of similar to looking at the weather on your TV, right, with your high pressure and your low pressure systems. Because that high pressure is where it is sinking back down, or no, sorry, it's where it's rising up, and then the low pressure is the other way, right? So that's what's going to create our global climate, right? And I love pictures from space for this because that's right. When you think about, if I look outside right now, it's gray and overcast and I can't see the sun, but my cloud here fits into some more of these big bands and these big cycles that are happening all around the world. And the whole reason that's happening, the whole reason why these clouds are shifting and these air currents are shifting is because of that temperature gradient. That extra energy, that extra heat at the equator is trying to get north. And it takes, as you can see, all of these swirls in the clouds, the most convoluted path, so it seems, to get that energy to do that. And so climate change, when we go back to that big grand word, is about this idea of what happens to our world when you start messing with that gradient. So if we all of a sudden don't have this really strong distinction between cold and hot in our center, if that's gone, what is going to become of our world? And this is where we can start zooming in and start looking at that sort of a little more locally and a little more place by place. And I will say that that answer has a lot to do with that gradient, well, and how that changes has a lot to do with where you are on the world. And it depends whether you're close to land or sea, whether you're in the northern hemisphere or the southern hemisphere. And the big reason is because it has to do with the ratio of land to water. So what I mean by that is that, if we just zoom in, we can just go imagine a nice coast somewhere and you're sitting on the beach in the daytime. And in the daytime, it's nice and hot and you've got that cool sea breeze coming in to cool you off. But then at night, if you're still sitting there, then you've got this warm breeze and it's actually going out to the ocean, right? It does this switch day and night. And the reason why that is because water takes way, way more energy to heat up than land. So what that means is that the air above land is going to heat up much quicker because the land is heating up versus the air above the water, because the water can take on and absorb a lot more heat before the molecules will heat up next to it or before they'll evaporate or things like that, right? So it's this idea, again, it comes back down to differential heating. So if you're in the southern hemisphere, then there's actually a lot less, can I go back to that? Oops, wrong way. So if you're in the southern hemisphere, right, there's just less of a land mass in the southern hemisphere. And so it's actually, when we talk about this 1.5, it's actually heating or it's heating less quickly than our northern hemisphere because there's more land in our northern hemisphere. And so the northern hemisphere is heating much more quickly. And so that has a big effect, certainly on our Arctic, right? Because the Arctic is essentially a shallow basin ocean just surrounded by land. And this land is heating up really, really quickly. So before, when I said the average is 1.5, so if we think about our North Pole, then from the 1950s to the 1980s, it was heating up at about 1.8 degrees Celsius. So it's already above our average, right? Or that's 3 degrees Fahrenheit. But then from the 80s to the 2000s, it's been heating up. It's now 2.5 degrees warmer than what it was in the 1880s, right? So it's heating up really, really quickly. And then so that's just one specific area, right? But that has a huge, this is that heat gradient, right? We're losing our heat gradient right now, and it's going to change our whole weather system. And we're actually already seeing that, right? So I'm going to zoom in and take a minute to read some of these. So what this is different climate anomalies from 2022, right? So these, when we just say anomaly, we just mean this is not something that we're used to seeing, right? So you can look, if we look sort of in along the US there, we've got a lot more hurricanes. There was Hurricane Agatha, Ivan, Fiona. And if we look at North America in general, this was the 15th warmest year, right? If we look at Madagascar, we have more cyclones happening, same with India. It was the 10th warmest year for Africa. It was the heaviest, heavy rains caused severe flooding in parts of southern China. And they were hit by the heaviest rains in 60 years. Japan had a huge heat wave. There were typhoons in the Pacific, right? Europe had the second highest yearly temperature on record. 2022, which I said before was the 6th warmest year we've had. This is just an example of these really extreme events that are happening right now. And it's not that these don't happen in nature, right? They do, but the frequency that they happen has to do with the stability of our climate. And the more we push it to an extreme, the more often these extreme events are going to happen to us. So let's go back to the report, right? So they're saying that for any given future warming level, many climate-related risks, like what we just looked at for 2022, are higher than they were assessed in the AR5. So that's the previous report. And projected long-term impacts are up to multiple times higher than currently observed. Risks and projected adverse impacts and related losses and damage from climate change escalate with every increment of global warming. Climate and non-climatic risk will increasingly interact, creating compounding, cascading risks that are more complex and more difficult to manage. So remember before when I said that climate is a part of this jigsaw puzzle, right? We had all those arrows and all those systems flowing together. So with that, right, as we keep pushing and pushing our climate, we're going to push those other systems, and they interact and they play with one another, and they're going to keep pushing one another to further and further extremes. So this is, I don't know if anyone's ever read it. One of the books I really like is The Dispossessed by Ursula K. Le Guin, and it's, well, I think it's mostly about anarchy, but putting that aside for a second, it's about a lot of different things. It's a really great book. You should read it. But one of it, there's a delegate from Earth in this future, and Earth has already been ruined, right? And they're talking about this planet, or they're there as an ambassador, and there's just this really sadness that they didn't make the changes in time. And so the ambassador is hoping that this planet that she's at will make those choices. And I always think about that. I come back to that scene in that book often when I read through things like this. And so it was really interesting when I came across this. This is a projection of what different regions in our world will be like. This is an extreme one. I'm going to tell you that now before I go through the examples of what different regions in our world would be like if our globe becomes 4 degrees warmer than what it is now. So this is an extreme example, but I just want to show you some of these things, right? So let's look at Peru. Peru is deglaciated, it's dry and uninhabitable. The Amazon is now a desert. If we look, Patagonia is melted, glaciers are gone. Africa has become mostly a desert. Most of North Africa and the southern US is pretty much inhabitable. and it's only just used as a solar energy belt that's going to stretch for thousands of kilometers, and that's going to be the source of power for us at that point, because there's no way to inhabit there, so it's the only thing left for us. The southwest US has become a desert. If we go look at somewhere like Australia, right, the only place that's left inhabitable is the far north and Tasmania. There are these really compact cities where the crops are grown. The rest of the continent is given over to solar power as well. New Zealand would become unrecognizable, just this really highly populated island, because it's one of the few places that still has a decent climate. And all that red that you see, I know that red doesn't seem like a huge amount by land, but all that is underwater now. So Polynesia, that would be completely lost underneath the sea level rise. And let's look at China. Dried rivers and aquifers mean this region has been abandoned. Intense monsoons have helped erode the land, leaving a dust bowl, right? So the extremeness of it, this is a big jump, right? This isn't jumping to 1.5, but this is showing what those jumps can lead to, and the significance of that. And so, interestingly enough, so this is a projection, right? This is not what's going to happen, but it's an idea of what the climate, what the world would end up looking like, and so how it is we'd have to survive to get through that. And oh yeah, so I guess I didn't talk about, so right, so Southern Europe becomes desert, but then the north, places like Canada and Russia, right, what was more or less boreal, subarctic, and Arctic is now becoming the proper growing conditions for world subsistence, right? So again, it's not everywhere has gotten worse, but it's just this idea that all these places that we know now would become largely decimated, right? A few of them would be okay, but certainly not all of them. And so we've been making projections about rising climate or rising temperature for, I would say, certainly at least my whole lifetime, and longer ago in the past than that. But we're making all these models, right? And so in the 90s, so different European ministers got together and they were looking at what was an acceptable amount of risk. How much change did they think that the world could handle and we would still be okay? And they sort of settled on 2 degrees, actually. They said, so in 2010, it was a UN official policy that governments agreed to hold the increase of global average temperature to below 2 degrees. And the reason that it's actually set at 1.5 today has to do with those smaller islands, low-lying countries, right? Because they felt like if they let it go to 2 degrees, much of their homes would be lost to sea level rise. And so they actually commissioned some of their own research, or sorry, some additional research, and to show that if they could stop it at 1.5, they'd actually have a fighting chance. So to put some numbers behind that, so that it's not just a vague notion of the sea levels rising. Come on, click through. There we go. Oops. What happens when it freezes? There we go. All right, so these are some differences if our world rises between 1.5 degrees versus 2 degrees. So if it only gets to 1.5 versus 2, there will be 10 million fewer people who lose their homes to sea level rise. There'll be 2 million square kilometers of permafrost that's going to be saved over centuries, and 50% reduction in our global population experiencing water scarcity. And our Arctic is only going to have a 1% limit on sea ice. That's a tongue twister right now. Sea ice-free summers. So the idea that they might still happen, but they're only going to happen 1% of the time. And that last one there is that we'd have a 50% reduction in species losing half of their geographic range. So before, that range is going to decrease, right? But if you can cut down how much that temperature change happens, the range is going to be less. And these are kind of unwieldy things to think about, I think, in some ways, because it's all relative, right? So, but it's just the fact that there is a difference to people and to animals and to organisms and ecosystems. If we can, every 0.1 of a degree counts, right? These numbers represent the lives, human or otherwise, that will or won't be changed depending on how much our climate changes in the future. And there's one other way I want to think about this, because when when the world says we don't want to hit 1.5, or we say, okay, well, we're okay to up to 1.5, like that's the threshold, right? And so every one of those degrees count. But if that's sort of the acceptable limit, we've already accepted losses. We've already accepted these changes that have happened because we can't undo them, right? And so when we think about what it is we're accepting at 1.5 as this maximum, it's things like this. It's that, if the world warms to 1.5 degrees, 14% of it, or excuse me, 14% of Earth's population is going to be exposed to severe heat waves at least once every 5 years. Right, so there was a really bad one in Europe, was it last year, the year before? There's been bad ones in North America, but those are going to just become once every 5 years. That's something you can just expect if our climate warms that much, right? And I said that when we think about it, that was a European example. We can expand it out. So if the whole world warms by 1.5 degrees, it means everywhere in pink has warmed by about 3 degrees, right? And our Arctic, which I said right now is about 2.5 degrees warmer than what it was in the 80s, is going to be about 5 degrees warmer than what it was. So, Arctic is really productive. I know we don't think about that because it's frozen so much of the year, but there are animals that fly up there, make these huge migrations to participate in the productivity, right? So it's going to shift the ecosystem. In that case, maybe there'll be more of it, maybe less, right? I don't want to say that everything that's going to happen is going to be bad, but there's so many changes that are going to happen. And we know that, if we look at that map of that 4 degrees one, for most of the area, it's going to have serious consequences, right? If we step away from temperature for a minute and think about water, right? So the reliance on water, well, one, if we think about it from agricultural perspective, we have hotter temperatures. It means you're going to need more irrigation, more water consumption in general, right? So this is a projection for the 2040s of which places, right? The darker the red, that's extremely high water scarcity versus, right, and you go down blue. So you can see that a lot of places are going to start having unreliable sources of water, which is a scary notion, right? Because that is our most basic need. And in sort of a sick twist of fate, in the same way that a lot of regions are going to be experiencing a shortage, other regions are going to have extreme flooding becoming more and more common. So places like Alaska and Western Canada, Eastern Canada, Greenland, Northern Europe, Northern Asia, mountain regions like Tibet, right? They're going to have higher and higher flooding because they're going to have these really intense precipitation storms come down, or precipitation events that are going to be shorter, or not shorter, but more intense. We're already seeing this in lots of places, right? And it's not that there's not the same amount of water. You could say that, within the year, it still gets the same amount as it did maybe 20 years ago, but the issue is the when and the how it's getting it. If it's coming down so fast and so intensely that has no time to sink into the earth or really, participate in the ecosystem, it just completely submerges it. In this case, that's an extreme version, but just in general, right? Water needs to have time in an ecosystem to play its roles, and floods, not just for the destruction they cause in that moment, but it's the effects outside of the initial flooding as well that have really long-term impacts. If we think about biodiversity and our ecosystems, right? So if we are at 1.5 degree warming, you're going to be looking at about 6% of our insects and 8% of our plants, as well as 4% of our vertebrates are going to have their geographic range reduced, right? And so it might not seem like a lot, but depending on where you're at, a lot of these are our pollinators. A lot of these are our endemic species, right? They only live in these small regions. And yes, the ones that are able to survive as generalists might push through, but these ones that have really core sort of niche roles in their ecosystem, those ecosystems are going to be gone, right? So if we kind of zoom out and look at it less from the organism perspective, and we actually just look at it sort of spatially, we're looking at about a 7% shift in biomes. So it doesn't mean that they're going to be gone. It just means that for 7% of our land mass is going to change from one type of biome to another, right? And one thing when you study biodiversity is that it's all about edges, right? Usually it's where you have two different things interacting that you get the most amount of biodiversity, right? And so if we're going to start having these edges shift, again, some of these are going to be it's such a tricky one saying better or worse. I actually really hate that perspective because usually if something's better for one person, it's usually worse for another. So it's all about perspective, right? Nothing's really better or worse at the end of the day. It's just a change. And I could even apply that to climate change as in general, right? Some people, right, if you really want to zoom out, the climate is going to change, and we're worried about it because we don't know exactly how. And we know we have some predictions that don't look so great. And if you are a desert animal, maybe all of this is really great, and all of this is projected for the next 50 years is fantastic, right? But if you're a human, this change is not such a good thing, right? And so I think that's important to keep in mind is we're always looking at these things from our perspective of good and bad. And then also that perspective of good and bad is different depending on who you are. So it's an interesting one to reflect back on. But anyways, so the biomes are going to change. I'll leave that tangent alone. All right, the big one in the room, which we haven't got to yet, is sea level rise. So if our climate is going to warm by 1.5 degrees, that means that we are projected to have a 0.1 meter sea rise level in the whole world. Again, it doesn't sound like a lot, but here's this community. Here's a really great example of what 0.1 is, right? It's only the darkest blue there, but that's going to be several people's houses. And on one hand, you might say, well, it's only a few people's houses, but this is a few people's houses all around the world. And that's somebody's home that means certainly a lot to them, right? And then if we let it rise by, if the climate gets up to 2 degrees, then we're going to be looking at around a 0.2 degrees Celsius change, right? So again, the numbers don't sound like a lot, but once you scale it down, you can see how that comes into play. All right, so let's keep this in mind. So what does that graph show here? Let me just move this for a second. All right, so that shows 1.5 for this one region. It would go up to about 100 meters, right? And this is just a little neighborhood. It's just an example set. Now here's something that is a bit more dramatic, is that if we do get an increased warming and it exceeds 1.5 degrees and it does get closer to 2 degrees, then we're certainly going to have instability in the Antarctic ice sheet, but we're more than likely going to have the irreversible loss of the Greenland ice sheet. And that would lead to about 6 feet or about a 2 meter sea level rise, right? That would change the coastlines of our world drastically. I'm going to say the word forever, but certainly, which is not true, it's not forever, but it's going to be on a time scale of thousands of years, which is going to be longer than any of us will have a chance to see, right? So it's that one is a big one. We would really like for that one to not happen, I think. All right, so that's what's happening sort of at the surface. Now, what about some of the things in our oceans, right? We're a big blue planet. So far, we've just been talking about this in land because we live in land. We've been a little bit human-centric, right? But it's going to make a huge, huge difference to our oceans, right? As I said that it takes a lot to heat up water, to the same point to heat up that air, right? And so our ocean temperatures, if they rise, they're going to absorb more carbon dioxide in them. It's like having a bottle of pop, right? It would have more bubbles in it. It's kind of one way to think about it. And so with that, it makes it more acidic, just like your bottle of pop. Or sorry, I guess everyone would say soda pop. We'll call it an even one, right? So with that, you're getting a rise in the acidity. You actually have lower oxygen levels. If we get to 1.5 degrees Celsius as a global warming, probably it's predicted between 70 and 90% of our coral reefs will die off. These are huge hubs of biodiversity and life in our oceans. They're the cradles of our oceans. And to see their loss would be devastating, right? Another thing which happens now, but would happen in much more significant range or area, would be dead zones. There would just be areas of our oceans that could no longer be productive anymore, right? There are places where it happens to seasonally. There have been things that have happened, right? But they haven't just been permanent. But that's what would happen, is there are places that the way that the mixing and the environment would end up is that they would just be a permanent dead zone. Which to me, who finds the ocean such a joy, is a heartbreak to think about looking into the future. And then if we zoom in and think about our sort of less on the ocean side, but if we shift it into more things like food production, right? So there are huge risks that come with that rising temperature directly to us as far as human health, our livelihoods, food security, right? So, and unfortunately, those risks are pushed more towards on those that are in poverty and that already have disadvantages, right? So an interesting one is shifts in crops, right? So the productivity in some range areas would go up, but a lot of it would go down. And things like rice, maize, these primary crops that feed so much of our world, right? The ability to grow those is going to be challenged under higher heat because, again, a lot of those crops are going to rely on that high amount of water, which it's just not going to be there anymore. And even range cattle, right? So the places where that's probably going to decrease by about 7 or 10%, which is a huge amount of food reliance, right? Unless you work in one of these sectors, right, you're often really disconnected from where your food comes from, or it can happen, not to imply that, sorry, right? So these are these things, these are these huge areas, these are these margins where it doesn't sound like a lot, but it's going to make a huge difference to our stability and to our food, right? And, you know, small ones that I think we can often take for granted are things like disease that go along with it, right? Warming climates is going to mean that a lot of things like malaria are going to be more prevalent because they're not going to have those cold seasons, those off seasons to offset them in places where we never had them before, right? Canada, which usually has a cold enough season that this isn't an issue, malaria could very easily be something that we have to deal with here. And so I realized that was a lot, and certainly maybe a bit overwhelming in some ways, but sometimes you kind of have to do it. You have to rip off the Band-Aid and you have to look at the wound and see how bad it is in order to take care of it, right? And to make some better choices. So I just want to read a couple more things. We're pretty close to the end here. So this is looking, again, sort of those responses. Some future changes are unavoidable or irreversible, but can be limited by deep, rapid, and sustained global greenhouse gas emission reduction. The likelihood of abrupt and/or irreversible changes increases with global warming levels. Similarly, the probability of low likelihood outcomes associated with potentially very large adverse impacts increases with higher global warming levels, right? Again, it's kind of a weirdly phrased sentence, but more or less it's just saying that if we can actually make a hard left on the choices that we make right now, it's going to make a difference. If we don't, then the likelihood of being able to change that in the future becomes harder and harder, right? As far as adaptation options that are feasible and effective today will become constrained and less effective with increasing global warming. With increasing global warming, losses and damages will increase and additional human and natural systems will reach adaptation limits. Maladaptations can be avoided by flexible, multi-sectoral, inclusive, long-term planning and implementation of adaptations actions with co-benefits to many sectors and systems. It's so funny because when I read these things, I always have to dissect them like 3 times in my head to get the whole intention of it. But basically, in order to change now, it's going to be pretty easy not to say pretty easy, it's going to be really hard to change now the behaviors that we need to stop ourselves from reaching these limits. If we think it's hard now, if we don't do it, it's going to be even harder in 10, 15, 20, 30 years, right? The longer that we take to change, can't teach an old dog new tricks, we're right on the edge of that, right? And the second part, this idea of sort of avoiding these not being ready for it, because that's what it means. Adaptation is not changing, it's not being ready for it, right? It's that you can't do it alone, and we certainly can't do it on a short term, right? This whole co-benefits thing, helping someone else to help yourself is really what this is, and it's hard to get everyone on the same page that that's what this would become, right? The Arctic seems like a sure long ways off for a lot of people, but the effort that we take to save the Arctic is going to have a huge impact on everyone else all across the world, right? That's where the basis of our whole climate gradient comes from. All right, last one, I promise. Climate change is a threat to human well-being and planetary health. There's a rapidly closing window of opportunity to secure a livable and sustainable future for all. Climate resilience development integrates adaptation and mitigation to advance sustainable development for all, and is enabled by increased international cooperation, including improved access to adequate financial resources, particularly for vulnerable regions, sectors, and groups, and inclusive governance and coordinated policies. The choices and actions implemented in this decade will have impacts now and for thousands of years. I could reread the whole thing, and there is some value in that, but it really, if you take one thing home from today, is that the choices and actions implemented in this decade will have impacts now and for thousands of years. So I'm going to stop us here, and I want to take a moment on this. And I want you to find yourself on the graph, right? This kind of shows all the temperature I've been talking about in the last couple hundred years. And it shows different lifespans, depending on when you're born, approximate age that you'll live to. And this is one of the figures that's out of the AR6 report. And this report, for all of its somewhat dry language, is really what it translates into is the voices of thousands and thousands of scientists screaming at the top of our lungs for someone to look this way and please care, because we're at a really, really critical point. And we're at such a critical point that, these scientists are still going to keep lobbying governments, and there's still going to be a big push for that. But they've also just turned directly to the people behind all these governments saying, please care now, because we're at that stage, we're at the threshold, we're about to cross it. It's only in the next couple of decades. And it's a tricky one, right? It's funny, we talk about all these big scale things, right? And even as I'm making this presentation and figuring out, putting the story together and putting my own story in context with it, it's like, well, what am I supposed to do, right? What am I actually supposed to do? And it's interesting, I've thought about this a little bit, and lots of people always talk about at the end, your actionable items of what it is you can go do. And 100% that you should, write your governance, whether it's your state government or your federal government, you should get better at recycling and cleaning those things up. All of those things are true. But I guess the thought that came to me at the end of all this was that it's not necessarily always about taking up a cause. Sometimes it's about figuring out what you need to sacrifice. And it doesn't have to be this big dramatic thing, but if you look at where your life is on this scale, the sacrifices that we make right now, big and small, will have a huge difference for those who are coming after us. And maybe that is that you only go to the grocery store, or you go once a week and you go twice. Or if you are going to fly, and you are going to go on a trip, make sure that you carbon offset your trip, because you do have, if we can afford to fly, you can certainly afford to take care of the planet while we do it, right? There's these changes we need to start thinking about. But sometimes they're not even as complicated as that, right? It's the sacrificing of your personal time to take care of these other people near and far, right? And maybe that sacrifice of personal time is you go and clean up some invasive species in your community. And sometimes it's as simple as babysitting the kid of your single mom next door so that she can go to work, right? And it seems like a silly one, but it comes down to things like this, right? If you follow that care and you follow that thought through, if someone who's less fortunate than you, or not sorry, right, but right, if they're having a hard time, if you go help them, then when they go to the grocery store, they can have the chance to make the choice not to survive and buy the cheapest thing, but then they can buy the thing that came from somewhere good and didn't have low production standards, right? It's this huge, huge domino effect. And we're like the big red domino right now, where if we push the next one over, there are so many that are going to fall, and not in a good way, that it does make a difference. Someone asked me that at the end of our last episode, are the things that I will do actually make a difference? And the answer is absolutely. And they might not seem like it makes a big difference on the big scale now, but you start changing now, and we do need to change very quickly, right? But it's shoulder to shoulder, side by side, setting up what the expectation is of our community and society to take care of one another. And I think that is the sacrifice that we need to look for and to hope for to make this turnaround in the time that we need to. So with that, I will end us there. I could go on for far too long, and I will pass it back to you, Rob.
All right, thank you, Kristina. Now, before we get to the question and answer session, I would like to remind everyone that you can submit your questions via the question field in your control panel. All right, so let's get to it. So how does the sustainability of resources for overpopulation factor in with the impact of climate change?
Sorry, can you just, the sustainability of resources for overpopulation?
Yeah, how does that factor into the impact on climate change, overpopulation?
That's a very interesting one. It depends on what you think about as overpopulation. If you're thinking about humans in this case, most of the time, the rough estimate is that our carrying capacity of Earth is about 10 billion. If we get across that, then we're going to really be at the tipping point. Obviously we're at the highest population we've ever been at. And so my personal belief is that our population is on a crazy rise. I would probably argue, or at least I'm on one of the people that's in the camp, that it's not a question of resource availability, but of distribution and equality, right? It's not that there's not enough to go around right now, it's how we choose to use things. And I'm going to take a stab at something that might be unfair, but is something I've come across a few times in my own life, is I've gone, if you're someone who likes to buy flowers from the store, no offense, flowers are beautiful and wonderful, but a lot of those places, when you're buying them in the winter, they were grown on prime food production land. If we're in North America, it's usually in South America. If you're in Europe, it's in Africa. And so that land that could and probably should be used for food production was used to grow in beautiful bouquets, which again, I love a beautiful flower, but if you love a beautiful flower, dry them in the summer so they're a vase in the winter, rather than getting them shipped across the world, right? It's a cash crop, but that cash crop could easily be replaced with food, right? So it's about shifting what's important. I don't think that we're so overpopulated that we can't take care of each other right now, but it's what we're valuing that is what's really impeding us.
So referring back to the biome slide and the uninhabitable area slides, can you tell us how those relate? Because it seemed like they were in conflict just looking.
Yeah. If we're thinking, sorry, I don't know which slide when you're saying it uninhabitable. I'm guessing you're talking about the 4 degrees Celsius one, of the idea of these areas being unable to live in. I think that's the one you're talking about. So the biomes that I showed there is roughly where they are now. And a lot of them, let's just stick around the equator here, because I could go bounce back to them, but there's a lot of detail in all of those. So a lot of those now are sustained by high amounts of rainfall, right? But if we lose all the moisture there, then those are going to become uninhabitable in that sense. So yeah, it's a bit of an extreme one. It's a really big jump to get there, I would say, to truly uninhabitable. That would be something we might see in like 1,000 years, right? It's not that or maybe even longer. I'm not entirely sure about the time range with that, but you would see, what's the right way to say this? So like the climate of what's, say, in like the Midwest US now, if we were to follow that trajectory, would then exist north of me in Canada, in sort of northern Alberta, in that like 50-degree latitude range, right? You're just going to take the desert, stretch out the desert in the middle, and then have those same biomes just push to the edges is kind of what would happen, if that helps make sense. Sorry if that doesn't answer it perfectly clear, but I think that's where that's going.
Thank you for addressing that. I appreciate that. So let's talk about whether or not, what would happen if not every one of the highest populated countries participate in lowering their earth warming practices. If you have, say, 75% and 25% don't participate, what will that do? Will that really help us out?
Yeah, it's an interesting one, right? People, someone, actually, I'll be honest, my mom asked me this question after the last webinar. We had a very similar conversation, and it's 2 parts. Every little bit will count, right? So we were saying every 0.1 of a degree makes a difference. So whether it's where it comes from, right? And so there are obviously a few big key players, right? The top 10, the top 10 emission countries, if you were to get each of them to decrease, it would make a huge, huge difference, right? And so to be honest, we're in them. US, Canada, China, different ones in Europe, right? We are them, right? So if not all of us change, and some of us do, it'll make a difference. If none of us change, it sure won't make a difference. And the conversation that I had with my mom the other day, it's like a bully on a playground. If you see someone being mean to someone else, would you go and do it too just because someone else did? It's a silly comparison, but it's also kind of true. It doesn't, at the end of the day, it doesn't matter I mean, it does, but let's just for a second here. What's important is you look at your own values and your own choices and make sure you're doing right by what you think is right. It doesn't matter at the end of the day if they do or don't. I hope they do. I really hope they do. But you need to be accountable for yourself. And just because someone else is making bad choices, it's not a reason for you not to, just because you think it won't make a difference, because it will. It will make a difference at the end of the day.
What do you tell people to give them hope for those of us who are really frustrated by this? Are there a lot of efforts underway to help change people's mind? And how can I support some of these efforts?
That is a great question, and it's such a hard one. You know, I am like I'm worried, right? I'm not going to say that I'm not, that we're at this changing point that you can't go back from. I'm also really proud of how far we've come. The type of conversations I can have now versus 2, 5, 10 years ago are already vastly different in my short life, I would say. And so I think we're on the right path, but I am worried we're not getting there fast enough, right? So the hope part of this is to keep pushing, right? And it's okay if you get exhausted, it's okay if you get overwhelmed, and it's okay if you need to withdraw for a little bit and recover, but once you've recovered, get back up and keep pushing. And it's so hard, it's so hard to make choices and changes for something that you won't see, right? When if we go back to that graph of when we're born, we won't see whether we did it. A lot of us won't, right? And so you just have to go forward hoping that you did your best, right? That's what it comes down to, is that when you get to the end of wherever you fit on this timeline, make sure the choices you think you made are for the best. That's the only hope I can say. I know it's not a great one, but I hope that when I get to the end of my timeline, I can be proud of the choices that I made.
All right, thank you so much, Kristina. That's going to be the last question that we do have time for today. So I'm going to throw it back to you for some closing comments.
Thank you all, everyone, for joining me on this. I know it was a heavy one, and I know it's a hard one in lots of ways to come to and to come to terms with. And so I appreciate you taking the time to see a new way and learn a new perspective and go home with it and chew on it and share it, or maybe just think some things to yourself. But either way, thank you so much. And yeah, slightly more lighthearted. I did an unofficial part 3. We're going to talk about weather next week and how to interpret your own. So we're going to carry forward this a little bit, but in not such an intense way. So if you're interested in that, come back next week. But yeah, you know what? Everyone get up, go for a little walk, maybe eat a piece of dark chocolate, shake it off, and look for something to smile and look for something to change, maybe even today. So that is my wish for you all.
Kristina, thank you so much for taking the time to present for us today. And I would also like to thank everyone who tuned in today. If you're interested in information on how you can travel with NatHab, give us a call at the number on your screen or send us an email at info@nathab.com. Our adventure specialists are happy to help you out. Join us tomorrow for our next Daily Dose of Nature. You can check out this week's lineup, including registration links, on our website at nathab.com/webinars. We did record today's presentation, and we will have the replay available on our website soon. With that, I will conclude the webinar. Goodbye, everybody. We'll see you next time.